Welcome to CS 320, Chapter 10. Let's start by looking at this language, a to the n, b to the n. So here are some words, the null word, and then this means the n is how many times we repeat the a or the b, and this just means that we need an equal number of a's and b's. So the words are a, b, two a's and two b's, three a's and three b's, and so on. So let's go ahead and try to make a finite automata that might accept this language. Now, a finite automata, it means that it has a finite number of states. So let's say that we create a finite automata that has some states in it, and we're reading A's somewhere. And then eventually we'll switch and we'll start reading B's, and we'll land in a final state. Okay, so I'm just kind of trying to figure out, okay, let's see what we can do with this finite automata. So we have a start state, we read some A's, get to a certain point, and then we switch and we read the same number of B's and we land in a final state. Now, this finite automata, let's go ahead and assume how many states it might have. I don't know, we'll just come up with a number, say 100 states. Now let's take the word a to 100 and 5, b 105. Now this entire finite automata has 100 states. So as we read these a's in the beginning, we can't visit a new state for each letter because eventually we're going to read 100 letters and we're going to have to go back to a state that exists before. So we need to, somewhere in this finite automata, there needs to be a loop. So maybe either a loop that goes like that or a loop that goes to another state that goes like that. But some way where we visit a state before, okay? And that's because we only have 100 states. There's 105 A's. Eventually, we're going to have to revisit a state we visited before. So let's say here's that loop, okay? And that's just reading the A's. We still have to read all the B's somewhere, so there probably is another loop over here. But let's say that we get this finite automata that we created to accept the word A to the 105, B to 105. So 105 A's followed by 105 B's is accepted by this finite automata. Now this finite automata had to go through this loop at least once before landing back into the final state. Okay, now let's assume, now that's just reading the A's, it would have had to go through this loop. Let's assume that we do the exact same path, except for we do this loop 2 times and then continue to the final state, or 3 times and continue to the final state, or 4 times and continue to the final state. As we're reading the A's, that means we're going to end up reading more and more A's, and that means this finite automata doesn't just accept the word A to 105, B to 105, it accepts another A to something larger than 105, B 105, because we just went through the loop one more time, but we followed the same path after that loop to that. So we'll end up getting more A's than B's. So there's no way that we could create a finite automata to accept the language A to the n, B to the n. And what that means is that A to the n, B to the n is a non-regular language. A non-regular language is a language that cannot be defined by a finite automata, a transition graph, or a regular expression. We just can't find a way to define it. And now you have to be careful here because maybe you're just not smart enough to think of a way to define it. But in this case, we proved it mathematically that if we have a finite automata that has a finite number of states, 100, and we take a word that has more than 100 letters in it, that means that word has to go through a loop. And we just do that loop again and again, and that And as we do that loop again and again, that creates words that are not in our language that the finite automata accepts, but it shouldn't. So that's our proof that a to the n, b to the n is not regular. Okay, now you might make the case, well, maybe 105 states isn't enough. So maybe let's say 1,000 states is enough. Well, then I'll just use a to 1005, b to 1005, and make the same argument. So really, it has to have a finite number of states, but eventually it stops. But our language can have more letters in it than the finite automata has states. So this argument will always hold. Now, one thing with languages is all finite languages, and remember finite means that we can count them and eventually we'll stop. So all finite languages can be defined with a regular expression. So the reason why is, well, if it's finite, then what I can do is I can write out all of the words, write out the first word, and then OR it to the second word, and OR it to the third word. And eventually, I'll finish writing out all of the words, and I'll have a regular expression that defines the language. So all finite languages are regular, but languages that are infinite, like a to the n, b to the n, there's no upper limit on what n can be, are where we have to worry about whether or not it's regular. Now, there are infinite languages that are regular as well, like A star, right? A star, there's no upper limit to how many A's we can have. So that is an infinite language. There's an infinite number of words in the language. But all finite languages are regular. So let's generalize this proof that we did for a to the n, b to the n, and we're going to generalize it into another proof that's called the pumping lemma theorem. You can find the pumping lemma theorem, which is in Theorem 13 and 14 in your book, along with the proof. Now, you can read over the proof, but it basically follows the same logic that I used to prove that a to the n, b to the n was not regular. But what we're going to use this pumping lemma theorem for is to prove other languages are not regular. So if we look at this pumping lemma theorem, first it says if L is regular, then what we can do is what I call pumping the word. And so notice it says if L is regular, then you can pump it. So if you go back to your propositional logic, if it's regular, then we can pump it. So how we're going to use this as a tool is we're going to say we cannot pump it, so the language is not regular. And if you remember that, that's modus ponens law that says that if this is not true, then this cannot be true. Now we got to be careful because a lot of times we see, oh, we can pump it, therefore it must be regular. But that's not the case. If you can pump it, it doesn't mean that the language is regular. But if the language is regular, then that means we have to pump it. So if we cannot pump it, then the language is definitely not regular. And so that's how we can write a proof to say that a language is not regular. Now, sometimes the weak version of this pumping lemma theorem doesn't always work. For example, we have a language like A star or A to the n, B to the n. Now, just so you know, this is not part of the regular expressions. You cannot have these exponents as regular expressions. But it does give a good idea of what I mean by the language. Any number of A's or one of these words that has an equal number of A's and B's in it. Now we know this is not regular, but this part is. And we can actually pump any word from this part, but we can't pump words from that part. So if we can pump a word, which this weaker version says, then we might be able to assume, or we can't use it to prove that a language is not regular. But this is a little stronger because it says it has all words right here, all words that are a certain length with more states than the finite automata has. So that all words says, not only do we have to pump words from this one, we also have to pump words for this one. So sometimes we might need this stronger version because we can find one word that we can pump, but this says we have to pump all words that are bigger than a certain size. And that size is just the theoretical size of the finite automata. So now that we kind of understand this pumping lemma theorem, let's go ahead and use it to prove that a to the n, b to the n is not regular. Now, the one thing I didn't really cover about pumping lemma theorem is what are this x, y, and z, and what does that mean? It basically means that we could take a word, and let's go ahead and use a word from A star. So here's a word from A star, and it says, go ahead and divide this word up into 3 parts, okay? 1, 2, 3. And we could call those parts x, y, and z. Now, we could have x being the null word and z be the null word, but y cannot be null. So we could divide it up so all of this is y, and then x is nothing in front of it, and z is nothing behind it. But anyways, divide it up. Then what we do is we take the y part right here, and we make copies of it. So now we can go A, and now this will come down and we'll make 2 copies of it. And then finally include the A down there. So what we have is the Y got copied to 2 spots and the X and the Z have to stay the same. Now this comes from the loop in the finite automata. So this is still a word in A star. So we're able to pump it. What we trying to do is find a way to break it apart into 3 parts so that we can repeat the middle part as many times as we want, and that still creates words in our language. However, let's go ahead and try A to the n, B to the n. So we'll have some A's here, and that's 4 A's, and we'll go ahead and have 4 B's. So this is a word in A to the n, B to the n. So let's go ahead, and there's things that we can choose. There's lots of choices for Y. Y could be 1A, it could be multiple A's, it can be all the A's, it could be some combination of A's and B's. Y could be 1B, and Y can be the very last B, and then we can have this be the X and the Z. So basically, I'm just figuring out, okay, what can Y be? We really only have 3 choices for the Y. The first choice is that Y is all A's. Okay, so that means it's either one of these A's or all of the A's, but something that just has A's in it. Okay, the other choice is Y is all B's. So as I choose my Y, it can be one of these B's, it could be all of the B's, it could be the last B, it could be the first B, but all I'm saying is any choice that has Y being all B's. And the last choice is some combination of A's and B's. We can have 1 A and 2 B's, we can have an equal number of A's and B's, and the X and the Z just fill in the other parts that Y isn't. So those are the 3 choices we have for Y. Okay, now that we've made all of those choices, when we pump it, if it's all A's, then we're going to have more A's than B's, and that word is not going to be in the language. When we pump it with B's, same reason, there'll be more B's than A's, and that won't create more words in the language. If it contains A's and B's, that means it's this part right here. And that means that our word is going to kind of get messed up. We're going to have words that are not the right format. So we're going to have more AB substrings than we need. Notice this word only has one AB substring, and it can only have one AB substring. So I can't choose a Y that is all A's. I can't choose a Y that's all B's, and I can't choose a Y that has A's and B's. There's nothing I can choose for Y. So I cannot pump it. Okay, since I can't pump it, because I cannot pump it, using modus ponens, that means that it is not regular. So this implies it is not regular. Now, the only reason why we have the pumping lemma theorem is to allow us to prove that certain languages are not regular. So the pumping lemma theorem is a tool that we can use to help prove that languages are not regular. And how do we do it? We prove that there is no way that we can pump certain words. And if we can't pump certain words, then it is not regular. So again, going back to the theorem, if it's regular, then we have to be able to pump it. If we cannot pump it, then it cannot be regular. And so that's our full reasoning for doing the proof. So let me cover the full proof of why a to the n, b to the n is not regular. What I'll do is I'll explain it first, and then I'll write it out and show you it all written out. So why is a to the n, b to the n not regular? Well, when I take words of the form a to the n, b to the n, we're going to have a certain number of a's and an equal number of b's. So now I need to choose a y that cannot be null and that is a substring of one of these kinds of words. My choices are one of these three choices. I can either choose a Y such that it contains all A's. Now it doesn't have to be all of the A's, it could just be one of them. It could be three of them, but it's just made up of all A's. And so any Y that I choose that only has A is going to fall into that category. And then I can do the B's. Any Y that I choose that only has B's is going to fall into this category right here. And then lastly, I can choose a Y that contains some sort of combination of A's and B's. So it contains both A's and B's somehow. So no matter what you choose for Y, and I'm trying to explore everything that I can choose for Y, no matter what, it's either going to have all A's in it, all B's in it, or some combination of A's and B's. If I chose A's, if I chose a Y that is all A's, whenever I make copies of Y or pump it, so I make two copies of Y, that means I'm going to have more A's than B's, and that's going to produce a word that is not in A to the n, B to the n. When I pump the word, it has to be in the language. Now let's try um, uh, B's. And kind of for the same reason, if I choose a Y that only has B's and I make copies of Y, then I'm going to have more B's than A's, and that's not a word in A to the n, B to the n. And finally, if I choose a Y that has some A's and some B's, I'm going to end up with a garbled up word that has too many A, B substrings. It's not going to be the right format. So that also won't be a word in the language. There's nothing else I can choose for Y. It's either all A's, all B's, or a combination of them. I can't pump this no matter what. Because I cannot pump it, it cannot be regular because if it's regular, I have to be able to pump it. So that's basically the theorem of why a to the n, b to the n is not regular. Now here's this argument all written out. If a to the n, b to the n is regular, then we must be able to pump it by theorem 13, which is the pumping lemma theorem. Words in a to the n, b to n look like this. When we try to pump it, we have three different things we can choose for Y. If I choose Y to have all A's, when I pump Y, it'll make words with more A's than B's, which is not in A to the n, B to the n. Same if I choose a y that has all b's. It will have more b's than a's. If y has a's and b's, when pumped, it'll have too many a, b substrings, meaning it's not going to be a word in a to the n, b to the n. There are no other choices for y, so I cannot pump a to the n, b to the n. Therefore, a to the n, b to the n is not regular. So there's a proof, and again, you can write it out in lots of different ways. There's no correct answer, but a couple key points is, one, there's nothing else I can choose for y. It's either going to be one of these three things. So I eliminated all the choices for y. I proved no matter what I choose for y, I can't pump it. Since I can't pump it, it's not regular.